Will I curve the test if most people do bad? There's potential for things to happen if a lot of people do bad. Well, we'll talk about what the matrix is first, and then we can decide. Dynamically allocated multidimensional arrays in C++ are kind of a little bit of pain in the butt. We'll get to that. All right, links in the chat. Yeah, we'll go over the test later. All right, so an expression tree is a tree. All the leaves are operands, and all the internal nodes are operators. Is a full tree. It's one of the tree descriptions we saw last week, week before. So one where it's full tree is kind of a strange description, but all right, doing a post-order traversal. Generate a reverse Polish expression that could be used to evaluate tree. All right, start off with a simple one. All right, 2 plus 4. We're going to do a post-word traversal. All right, post-order traversal on the above. We get 2, 4, and plus. All right, and that would yield 6 as our answer. Let's make alert. Ugh. Try that again. All right, so the tree itself handles operator precedence. All right, I can't add 4 plus and multiply. All right, so in order for us to add this part of the tree with this part of the tree, first have to evaluate the subtree. All right, so 5 times 7 would happen first. And then we would add the result of 4 there. And if we do the post-order traversal, we'd also see the behavior, right? So our post-order traversal. First leaf is 4, then 5, then 7 makes multiplication a leaf effectively, and then we add at the end. Our answer, our stack states we have 4 on the stack, we have 4 and 5 on the stack, 4, 5, 7 on the stack. We multiply, gives our 35, and then we add, giving us our 39. All right, so going from an infix expression to a tree. Right. One, go ahead and step 1, turn the operands into leaves. Step 2, join leaves together based upon operator precedence. All right, so say if we want to have it, well, all right, so we have 1 times, 1's bad number, 4 times 3 plus 5 divided by 10. All right, so mathematically, this will be 12.5. We want to make the corresponding tree for that. All right, so first step is create a leaf for each operand. Keep them in the same order that they appear in the expression. All right, 4 times 3 will be the first expression to be evaluated. So go ahead and create a node joining 4 and 3 together with the corresponding operator. 5 and 10. Would be the next operation. So we'll build that part of the subtree. And then these two terms can be joined together. At the end. Yeah, looks like I lost my numbers. All right, so let's check. Check that our tree is generating the correct math. All right, so post order. I have 4, 3 times 5, 10, divide plus. So we'll have our stack states. 4, 4, and 3 multiplied together. And 5 gets pushed, 10 gets pushed, divide, and then add together. It's probably the easiest bit of trees that we have in the trees section. Any questions about trees? Any of the trees stuff that we've been talking about? And we got our self-balancing binary search tree known as AVL. All right, our B trees, 2, 3 being our small example. Another self-balancing tree structure. Binary heap, also self-balancing. Looks like there aren't any tree questions at the moment. We're gonna go over the implementation of it. No, we don't need to do. It's just a binary tree. Nothing terribly exciting about it. It does make a post-order traversal quite useful. Post-order traversal is also a way we would destroy a tree. It's one of the ways we could destroy a tree. All right. Graphs. Graph is a collection of vertices and edges. All right, so trees were specific types of graphs. They are directed acyclic graphs. There can be several types of graphs. A simple graph would be our default type of graph. Edges are all bidirectional. It's going to be a set or a non-empty set V of vertices and a possibly empty set E of edges. All right, so let's talk about some more terms here. So vertex. And this is basically, a node or a point in the graph. Typically, a vertex will have a label associated with it. And we have an edge. An edge defined as a pair of vertices, right? It determines that there is some sort of relationship between the two vertices. Two vertices that share an edge are known to be adjacent to one another. An edge may be directed, may also have a weight associated with the edge. And so the weight, aka cost or distance, among many other terms, is data that is relevant to what we're trying to store. Right, so i.e. distance, cost, right? How many frequent flyer points may get, etc. No, and there's a very massive one line of code difference between the matrix being directed or not directed for building it. Okay. Simple graph examples. All right. Sample one. And we have a graph. There it is in all its glory. It's the smallest existing graph that we can create. Sample two. And we will label the graph. Vertex, which will be common because that's easier to refer to a node if it has a name. All right, third graph, two vertices, still no edges. Connecting them. And now we'll start with our edges. Four graphs. All of them are just simple graphs. And we'll get bigger graphs later. Uh, there we go. Gotta remember my shortcuts. A directed graph. All right, so it's going to be a collection of vertices and edges. There exists at least one edge that has direction to it. All right, so let's compare. In a simple graph, the edge AB is equivalent to the edge BA. In a directed graph, AB and BA are separate edges, even though may just show it as a single line. All right, so our graph's going to have to get more complicated here. Can I just have single vertex? And we'll bring in arrowheads here. Again, it's not going to be too common. We will not bother to label things. Typically, there's going to be a label. All right, so this graph has two vertices and one edge, and the edge is just between A and B. All right, so examples 3 and 4. are effectively the same graph. Two vertices A and B, two edges AB and BA, just two ways of drawing it. So example 2, we have my set of vertices equals A comma B. Set of edges is AB, and that's all there is to example 2. Example 3 and 4, we have our two vertices A and B, and we have AB and BA as our edges. Only difference is just the way that we're choosing to represent it as a drawing. Still the same graph. The way we draw a graph is immaterial. What a graph is based on its notation or the matrix that is representing that graph. Any questions at the moment? Everyone's brain's already drained from the test. Just how it goes. Lots of new terminology. Right? There's no difference between 3 and 4 other than the way that we drew it out, which is why putting them both here same way. So on that thread, let's talk about how we will actually represent the graphs in memory. Because the graph is not going to be processed as an image by an algorithm. There's three common ways to represent a graph. We will look at two of them. An adjacency matrix is going to be a square matrix where the rows and columns represent the existence of edges between pair of vertices. It will label top and left axes as the vertices. An edge exists. We'll set that bit to be true if we're just a simple graph or a directed graph. As we get to other graph types, we'll look at more complex element types, right? So our graph is set of vertices A, B, and C, and set of edges A, B, B, C, and we qualify that it's a simple graph. Corresponding matrix. Oh, one other thing here. Let's label axes are done in alphabetical order by convention. Right, we have three vertices, so the matrix will be a 3 by 3. We have fourth row and column, so I can put my labels in. All right, so if an edge exists from A to A, we'll just go ahead and set this particular index to be on, right? We have an edge from A to B. So A to B, and since it's a simple graph, B to A, the reverse will also be set to true, and we have B to C, and the reverse C to B. All right, and what we'll have for a simple graph is we'll have a mirror across the diagonal. All right, so simple graph will be mirrored across the diagonal. All right, example 2, directed graph. 2, 3 vertices again, and our edges just list that as the same. All right, A goes to B, and B goes to C. So there are two labels. There are two entries turned on. All right, if we draw either graph, and then there's lots of ways to do it. All right, we have A, B, and C. All right, that's one way that we could draw that graph. Could have put in C. I could have put C on the first side, on the left side. I could put C above B, below B. Could put C all the way or below A, right? And just look like I think that's like what they call the claw graph. There are a lot of different graph shapes. We're only to a subset of them. Well, I want you to some links for all the various other shaped graphs in case you're interested. And then our directed graph. It's pretty much the same thing, except we got some arrowheads. Oh, there's a snake. And that's an adjacency matrix. Each of these just bits. Anything that I left empty is a 0. So empty equals 0. And then adjacency equals 1. Yeah, so we have source and then destination. So this column, these would be the source vertex, and then this would be the destination vertex. The other approach being an adjacency list. Why is that an 11? Got too many digits. And adjacency list. Apparently I can't type adjacency well at all tonight. This is just going to be an array of linked lists. The array is the source vertices. Each element of that array is a linked list of the neighbors of that vertex, those that are adjacent. All right, so if we take the same graph, we build an adjacency list for it. Yeah, let's just update this guy. So we'll have an array A, B, and C. And we'll have our nodes. A goes to 1, so there'll be one entry here, and B goes to, oops. B goes to 1, so there'll be one entry here as well. Yeah, and there's our adjacency list for that directed graph. Let's make a bigger graph. If I can let go of this. Try to resize. Too close to the edge of the screen. All right. All right, let's get a few more vertices in here. Ah, poor C got lost in the shuffle. All right, we'll add D and F in here. And we'll add a few edges. If an edge in a directed graph does not have an arrowhead, then it is simply going both ways. All right, so number of vertices increased by 2. So this array has to be sized appropriately. A has an additional outbound edge, so we will add in that A, in fact, let me get rid of this edge over here. A has the neighbors B and D. All right, so very, very important thing to point here. B, the fact that it links to D here in the list has no bearing on the relationship between B and D, which is why I went ahead and deleted that edge. B does not have an edge to D. So this is not saying B has an edge to D. This is simply a collection of the vertices that A has an edge source as the source vertex to, and these are destination vertex. So A goes to B and A goes to D. Also note that we're keeping things in alphabetical order here in both the array and the lists. All right, so B goes out to F. Definitely, alphabetical order makes things deterministic. And as computer algorithms kind of very much rely on things being deterministic, we will maintain things in such a way. All right, so C has one outbound edge here. Be going to F. There only one outbound edge, so it has one item in its list. D has A and F. All right, so we will put A and F into its list. Again, A has no relationship to F, right? There's no edge between A and F. If we're going to traverse this graph from A to F, we're going to have to go via B or D to get there. And then F is the most popular vertex. It has B, C, and D all within its set. B, C, and D. So our in-memory representations. In-memory representation. Yeah, because they're linked lists. So we would be using a singly linked list, right? Singly linked list be the default. Implementation. Tation. And so matrix versus the list. All right, so the connectivity of a graph represents how many edges there are in relation to how many vertices. A low connectivity graph has few edges in comparison to the number of vertices. A highly connected graph will have a large number of edges compared to the number of vertices. All right, so for a matrix, if the graph has low connectivity, most of the elements in the array are 0. So we're wasting space. All right, so for example, we have a 100 set of vertices. For our graph, and the matrix has 10,000 elements. And if there are only 50 edges in the graph, it's a lot of wasted space. For an adjacency list, we have the same 100 vertices. The array is 100 elements. And then we'll have 50 nodes across the set of lists. All right, so we'll have a smaller footprint here. Footprint here. If we have a highly connected graph, the footprint of the matrix does not change. Footprint of the adjacency list will be growing proportionally to the number of edges in the graph. So while we're talking about this big O notation, right, we are now in a multi-term state. To be possibly using multiple terms, we'll be considering the number of vertices, which is denoted as pipe v pipe, and or the number of edges, pipe e pipe, in the graph. So for example, may see big O, B plus E sort of thing there. It's possible that that symbology is used for magnitude as well. You'll find that mathematical notations, there are overlaps depending on context. All right, so space complexity. The matrix is big O B squared nope. Let's make dot. All right. B squared space complexity of an adjacency list is big O, as we had above, V plus E. Right, however big, if we have 100 elements, then we have an array that's 100 elements. If it's 2,000 elements, we have an array that's 2,000 elements. Right, so that part grows directly proportional. And then the number of edges. If it's a completely disconnected graph, there are no edges, right? Then we'll have 0 here. But if every vertex connects to every other vertex, or if there's even multiple edges between pairs of vertices, right, then this is going to grow based off of how much that grows. All right, so talking about that, let me make sure we have easy access to our links. right? We're big into graph theory right now. This is where we are terminology. Pretty much all of this section in the class is about graph theory. Right? Our matrix, right? So you can see, interesting. All right, so here we have a graph. One way to draw this graph, and there's going to be a lot of different ways to draw this Ferris wheel, right? But the computer is going to need a way. You can see they have the diagonal there. So we have a mirror. You can draw straight lines across, get a mirror of things. All right, directed graphs, all fun stuff. So that just means the arrowheads are in place. It's possible every single edge has an arrowhead, but maybe it does, maybe it doesn't. Right, and then we have our adjacency list. Adjacency list. Right, no fun pictures over here. That's terrible. And again, graphs. Right, graphs are gonna be very, very uh, complex by comparison to trees. The ways some of the things that we're doing here, but graphs are very, very, very much in use. Right, whenever you go into Waze or Google or wherever you're using to get directions from here to there, that is a graph-based algorithm. You're trying to establish a path, specifically the shortest path between you and where you're going, right? Networking, routing tables are going to be maintaining themselves based on graph theory, right? Going to book flights from LA to New York. A lot of ways to get from LA to New York, and the shortest distance isn't necessarily the flight you're going to be booking, right? Because the direct flight from LAX to LaGuardia or wherever LAX goes direct to will be the shortest distance, but it may not necessarily be the cheapest flight, or you may not necessarily get the most points, or it doesn't qualify for using your rewards miles on that flight. So you have to go to Houston or Atlanta or Denver or wherever a particular airline's central hub is to get the costs down. Right, so you'll have functions like this where we're getting all the neighbors of a particular vertex. Right, getting all the neighbors of a particular vertex for an adjacency list is going to be pretty easy. It's basically here's the list, possibly as an array form or something like that. Doesn't have much work to do. You can basically give you the head and it's like there they all are. Testing to see if two vertices are adjacent. A matrix is going to work out better here because we can just index into the matrix based off of these labels and determine if those two are there, assuming we know what the indices of these labels are. That part can be add an extra layer of complexity. But for an adjacency list, right, we can go straight to X. This is where we are in our list. Then see if Y is a neighbor. That becomes a bit of a linear problem. Everyone kind of with me so far? All right, let's talk about the lab. Going to create a matrix. All right, so a two-dimensional array, which can be a little bit of a pain in the butt, C++. We're going to need two-dimensional array for the matrix, and then we'll have a separate array for the labels. Labels are going to be how we determine the index for the various operations that we're doing. Well, we can talk about extending the due date later tonight if we need to. There's really nothing new code-wise for this, but let me point you to a Stack Overflow dynamic 2D array. With the link in the chat. Right, they want to make a two-dimensional array with a new dynamically allocated. And there are a few answers in here. And if it's a compile time constant, this all works lovely and good, but we're not dealing with a compile time constant, so this doesn't work all well and good here. So what we're actually going to need to do is create a jagged array, which is this second part here. The lovely star star. I don't know if you remember star star from your C++ or C class or whatever it is. It's a pointer to a pointer. So it's an array of pointers where each element is in turn an array. All right, so let's demonstrate. All right, see out. How big is the matrix? And size, and then we loop. So this creates the outer boundary. So if they say 5, 10, 20, whatever it is, the outer array will be that big, and then we'll loop. And this changes from I to row. Row equals 0, row less than size, row plus plus. Yeah, star stars is one of the things I really don't like. It's one of the things we're talking about in the C class right now. We'll have to talk about it a few more times, I expect, because yeah. Right, so matrix sub I, or row, is a new int size. All right, so the first time around, so line 19, however many, whatever, my lines aren't so straight. All right, so new int size creates an array of whatever the size is. All right, so that gives us an array. And I believe I already forgot my pointer. Let's get that in there. Get my pointer star. All right, so each element is in turn a pointer. So the element type is an int star. So the outer dimension, oh, it's a collection of int stars. So inside matrix of 0 equals new int, basically create another array of the same size. Not very well drawn, but same size. 1, 2, 3, 4, 5, 6. Missed a slash because I obviously can't count. And we have a fun pointer. That points where this is in memory. So it's not actually a square matrix. It is a jagged array because each of these rows could actually be sized differently. All right, so if I were to do or less than size, nested loops, we can say, let's do a counter. Matrix sub row sub column equals counter plus plus. So if we go down like just the column, yeah, we'll just print all out. Spit it out. A little bit of white space. And end line after we're all said and done. Redeclaration of counters. Oh, obviously I copied too much. All right, so we did build a 3x3. All right, we got a row, and a row. 9 total elements.
Professor, what is the point of pointer pointers exactly?
What is the what's the point of pointers? What I say again?
What is the reason for having a pointer point to a pointer?
Because that's because you can't dynamically allocate, right? There's like int 2D equals new int size. And this the languages have changed. Right? If I try to do the same thing over here, let's see what it gives me for that. Right? See, needs it to be constant size, so we can't do this. Right? Some languages will allow you to do it like that way, do comma separated, but right now it's getting confused. It's one of the things that C++ don't do well. The newer languages do much better. Let's see, I missed another question. Yeah, so let's see what the lab said. Square matrix. All right, so you can see this is a directed graph based on my example. All right, so we added the edge AB and then BA. And then -1 to stop. And you can see we listed out the edges. All right, if this were a simple graph, we wouldn't be listing out the mirrors. Yes, this is very similar to what you're going to do for lab. You're just going to be objectifying it. All right, so let's get rid of that because that does not work. All right, so we want a 4x4, makes a 4x4. Oh, it's terrible. I need tabs. All right, let's do tabs. There you go, alignment. It's always nice when things line up. See how big we can get before we start blowing up the screen too much. Let's see. Well, a jagged array is a double pointer, right? Star, star. Star, star. Star is your friend. Just gotta remember that when you do a single dereference operation, then you're talking about a pointer, right? So what we do here is we're doing two. So we do our 0. That takes us to the first row. And then we do a 0 again, takes us to the first element in that row. There's other ways to go about it. It isn't necessarily always one best implementation. As long as it looks like a matrix, should be good to go, right? I mean, you could do this as an array, right? You remember the row major order stuff that we did, right? You could effectively just build the array. You just create the array as size by size, and you can do mathematical mapping of what a row versus what a column is on that math to index into the array. And you'll effectively achieve the same thing. As long as it takes the user's number at runtime, then we're good to go. All right, let's work. Let's go ahead and take 10 minutes. We can start cracking at this lab, and then we will get back to our lecture. All right, any follow-up questions? All righty. All right. Let's point out modules section graphs. All right, terminology, vertices and edges, as we've talked about. And the edge is either going to be directed or undirected. All right, so if you see a graph, no edges have an arrowhead on them, then that means every edge is going to be bidirectional. If you see an edge, in particular in the graph, then it's going to be bidirectional. All right, graph link, post that on the notes as well. Graph theory, that was posted up there as well. Peruse Wikipedia a little bit in the graph section. There's a lot there. There's a lot of a lot. Right. And we have quite a few more graphs to go over as we just begun the sections. Please check out these items. I'll post links again to that area in the announcements. Right, again, links to Wikipedia. All right, it's multiple places there in case you can't find things. Let's go ahead and get into graph shapes. All right, so some graphs adhere to particular patterns that denote particular shape. And there are many of these. Grab a link later. Oh, the graph shapes. Looking at our simple graphs. All right, so that means an edge will go both directions. All right, so a cycle graph is going to be a polygon, triangle, square, pentagon, etc. The degree of every vertex in the graph is going to be 2. All right, so new term. Degree, this is going to be a characteristic of a vertex. Is the count of the number of edges that touch that vertex or incident to. Another way to phrase that. So let's create a few cycle graphs. Point out the degrees of things. I'm sure some authors have minimum number of vertices for 2 here, where it's just a line going back and forth. Not really much of a cycle, but one can argue that it is. All right, so this graph, this would be a C3. There's my subscript. Can I get the subscript format? I have to copy from somewhere else, fix it later. Okay. To a C4. Make it more like a parallelogram or a rhombus than a square, but it doesn't much matter how we draw this shape. It's still the same graph. And our C5. All right, so the way the notation works, you'll have as a subscript the number of vertices. Oh, forgot to change my number. Number of vertices in the graph. This is one of the places where some of the graph shapes you'll see set variations in the definitions for what the numbers should be in all of our definitions. It's going to be the number of vertices in the graph. All right, so cycle graph, as is the notation. Cn, C stands for cycle, and N, the number of vertices in the graph. Uh, no dot dot dash station. Okay. All right. So every vertex in the graph, there are two edges incident with those vertices. So it just starts becoming a bigger and bigger circle, aka cycle. Star graph. It's going to be a graph, a central vertex, and n minus 1 vertices connecting to that central hub. Our notation will be S of n, S for star, and n for the number of vertices in the graph. right? So I believe some authors will go with here's an S1 at the central vertex. Find it a little bit ridiculous that any of these graphs, before really we get to four vertices, are considered to be much of a star. But we'll roll with it because some authors go that way. I don't really find it much of looking like a star until it gets to that point where we have four vertices. All right, so we'll have a central vertex in each of these graphs that everyone else will connect to. And so the degree of every vertex on the perimeter will be 1, and the degree of the central vertex will be n minus 1, right? So this is S4, and there are 3 edges incident with the center. We have an S5, gives us 4. Get S and all right, so NS1. I just paste I can. No, I don't have a text box. Okay. S2, S3, so on and so forth. And an S5. Right, so the degree of every vertex in a star graph is 1, except for the center. All right, that will be n minus 1, where n is the number of vertices. All right, so in other words, will be number of vertices minus 1. Wheel graph. It's the bit of a composition, a star graph within a cycle graph. So I'll basically take that drawing and start to surround them. All right, so not much in the way of cycle capabilities when we get to the first 3 parts. So I'm going to blow those bits away. Just drag this up. All right, so we'll take the star and drop a cycle around the perimeter and makes it a wheel. And I will change the S for W. And we can make it bigger and bigger if we want to. But it's pretty much going to look like if you have a bicycle, go look at your bicycle. That's a kind of a wheel graph. Right, if you were to go ahead and use the spokes as the edges, you'll have your central hub representing that central vertex, and then all of them connecting to the outside perimeter, making a cycle on the outside, a bicycle. Yep, over the test tonight. Still have 33 minutes. And wheel graph, degree of every vertex is 3, save for the center, which is number of vertices minus 1. Complete graph. Notation will be k of n since c is already taken. Degree of every vertex. And this graph is number of vertices minus 1. And so every vertex is connected to every other vertex. All right, so here we'll get some overlap. K1, one vertex, connected to everything else that it can't connect to, which there isn't any. K2 will just be two vertices connected to each other. A K3 will look exactly like a C3. And then a K4 will start to be something more. To a K5. That'll be big enough. Right, K1, K2, K3, and then a K4. Kind of starts off as a cycle. But then we'll add a couple more across. Lots and lots and lots of edges. So I need 4 edges for every vertex. That's not what I want. All right, those are connecting across, and this one will just wheel across that way. That's better, right? So this vertex has 1, 2, 3, 4 edges coming out. 1, 2, 3, 4. And then we have 1, 2, 3, 4. And then lastly, 1, 2, 3, and 4. Everyone connects to everyone. It makes for a high amount of connectivity. Wheel graph, star graph. Just 2 more to talk about. We have a bipartite graph. This is going to be a graph. A graph can be split into 2 distinct sets. The vertices in each set are not allowed to be adjacent to other vertices within the same set. And so you'll typically see this in a job matching problem where you have various employees and various tasks to be completed. All right, not every employee has the skill set to perform every task, and not everyone has equivalent efficiency in getting jobs done. All right, so we'll have two sets. Name of the sets are a little bit arbitrary, A, B, U, V. Seen different ways of being labeled. Then we'll have our various vertices. That's in each set. All right. Joe, Amy, and Anna's people, jobs, whatever. Let's say we're doing a demo, so someone needs to demo the kitchen. Someone needs to demo the porch. Someone's gonna demo bedroom 1, bedroom 2, and whatever living space. Right? Not all the rooms are necessarily gonna be the same thing. The bedroom should be easier if there's just doors, carpet, whatever, not much to take out of there. But we'll say that Joe can do those areas because there's no electrical or plumbing, and often there'll be weights associated with that. Amy do those particular jobs, and Anne can do that job, whatever. Arbitrary data. All right, so Joe, Amy, Amy, Anne, or Anne, Joe, there's no relationship that makes sense in here. It's possible we might end up having two people working on the same job at the same time. So that relationship will coexist by the fact that they're both working on the same thing. So the idea with the job matching algorithm, which when you get into advanced data structures, you actually talk about how to solve for this is how do we get this renovation done in the fastest way possible? And this is our data representation that we would have. And that is a bipartite graph. Yeah, so there will definitely be a algorithm that would associate with that, but it's beyond our purposes. All right, so a complete bipartite graph will mix the rules of a complete graph with a bipartite graph. All edges that can exist between the two sets are there. Our notation, we KAB, right? Set A is a collection of vertices. Set B is a collection of the same. A connects each vertex in A, connects to each vertex in B. Right, so the degree of every vertex in A is equal to the number of vertices in B and vice versa. So if we do have a job matching situation where everyone, right, say we're doing the framework of the house, and everyone's a carpenter, so everyone can work on the framing of the house. So we'll have data for every person to all the particular jobs of the framing that needs to be done. Try to figure out who's going to work on what section fast, right? Do we need 3 people for the living room or 2 for the kitchen, right? Basically try to distribute the resources in such a way that the job's done as soon as possible, right? We don't want people sitting around because they can't help because there's only so many people you can put on a particular job before diminishing returns gets to you and or it's just impossible for them to help. They're just going to get in the way. Let's raise graph shapes. There are a lot more shapes out there. It's not the kind of graph shapes I want. I'll find the link for that later. For now, let's talk about the test. Okay, you can now see what you did on your test. Reverse Polish. Should we take a 5-minute break before we get into this, or should we just knock it out?
I feel like
Knock it
knock it
out.
out.
All right, let's get it done then. Okay, so let's get our text. So we have our stack states, right? 5, 5, 4. Then we do our add. Then we push 3, 2, do our multiplication. 9, 6, 8 adds on. 9, 6, 8, 4. Then we'll do our divide. Comes a 2. We'll do our subtract. And then we'll do our addition. All right, so after the first addition, we have 9 on the top of the stack. And after the first multiplication, right, we have 6. Bottom of the stack, right, still 9. After a division, top of stacks are 2. And we have 13. Which following statements pertain to recursive functions? Yeah, stack overflow can happen. We should, yes, if we can just write the loop, we should rewrite it. Avoid using a whole bunch of stack space. Recursive function has a call by itself. Not every function is recursive. And indirect recursion. And we need some sort of base case to stop recursion from happening. Does it say not use it? Can we solve loop? Should be. Oh, sorry. Yes, I got that. I read that backwards. Let me uncheck that. No, we can definitely get a stack overflow. We can demonstrate stack overflow later. We'll get it into our bug question in there because it has a poorly written base case. Oh yeah, the orders aren't necessarily the same for the questions. Using each of the 3 methods, pivot. So we have 3. Right, we have first index, we have middle index, and then we have the median of 3. So automatically 55 and 34 make the cut. Now the question is one of those, is this the median of those three? It's not. So it's just 55 and 34. So those are two possible pivots depending on which of those three we chose. Selection sort, which we move next, right? So we have 8 already in its sort position here because that's the smallest value. So even if we were just to start from scratch, no state would change. So the next thing, right? 42 is smallest. No, 19 smaller. 11 is smaller. So 11 and 42 will swap, giving us 8 and 11 as our sorted part. Right? 22 is not the median. It is a value that is considered to be the pivot, but it is not selected as a pivot. All right, merge sort. Right, so we'll break down to 2-element arrays. That's sorted. 2-element array. That's sorted. 4-element array. That's sorted. So that we've done the first half. So we'll jump over to the right. 2-element sorted. Those two are not sorted. So these two need to swap. And it's 41 and 59. 4159. Merge sort and log in. Quick sort n squared. Selection sort n squared. N squared. N squared. Line 3 has a bug because that is a bad base case. Because if you call this with a negative number, that's just going to go forever. Recursive call line 6. Why would you ever call it? You can't control who's going to call your code. Anyone can call your code. Right? Ask user, give me a number so I can start dividing by 2. They type -5. That is a number. It's one of the things that you want to quickly get in the habit to is do not trust data. I guarantee you'll run into data that is not going to come in the form that you expect it to come into. Data is not trustworthy. If it's coming, it's going to come from a configuration file, a user, a socket connection, some sort of API. It'll work with non-negatives. Yes, because 1 divided by 2 is 0. So there's no remainder. And the fact that I kind of try to push people to this by doing this as a division, that this line of code has a problem. Some people will think that we'll never get to 0, which we would. Even if it was a float, we would get to 0 eventually. It would just take longer. But yeah, do not trust data. So you have to first verify that data is what it should be, or code in such a way that the multiple choice would have been graded. Okay, so 13, which flying sort swaps the most? Bubble sort swaps the most in the worst case, right? Take the first value, swap it all the way in. Reset. First value, swap it to almost to the end, right? One fewer, one fewer. Quick sort, you can get up there. Insertion is n at the most. Or sorry, selection is n at the most. Insertion doesn't swap at all. It does shifting and merge. Merge can get a fair amount of swapping, but not so much. It's not really swapping anyways. One could argue that, but it's still not. Bubble sort is going to win that. All right, math. Math, 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 math. Given the base address, 1400. What's 5, 6, right? So we have 5 rows at 9. So 5 times 9. Use the keyboard. That's just terrible coding. right? 45 elements plus the 6 for where we're in here now, each of which is 4 bytes in size, right? Plus our 1400 base address, 1604, and more interesting autofill options there. Let's see. More math. So I got the 99 times 4. Yeah. 99 times 4 plus 1400. 1796. And 32, so that's 1432. I could type. The base case. Oh, and cutting negatives in half. Oh, that's a good point. And negatives will go down to 0 as well, won't they? Ah, guess we're going to have to update the autograder. Fine point, 5 point. Everyone's going to probably get that one back. So 0 is now an acceptable answer for that question. All right, 0 is 1400. Number 18. Key shifting. So that's our insertion sort. Ugh. And let's see, 19. First line, that's incorrect. Insertion sort. So sorted array, 2 5's good. Then 2 5 9. So that would have been done. And this is looking pretty wrong there for line 3. The bug question, I think it was number 8, or was it number 11? Number 11. This is reachable in all cases, right? We'll test the code just to make sure. 20 pivots. So 17 happy. 45 is not happy, so it's the first one to get swapped. 24 is not happy, so those two get swapped. And we continue. So 24 is here and 45 is here now. Fine, that 51 is not happy. Let's go to the right. 88 is good. 14 is not happy, so 14 and 51 will swap. Find 35, not happy. Jump to the right. 35 is good. Jump over. So 35 doesn't move. So our partition split there. We have 35, 51, 88, and 45. It'll be the right partition. We have 17, 24, and 14 as left partition. Right, 20, if we were to keep going, 28 would come in here, and then 14 would end up over there, and we have our division. Let's see. Add. Add to head. All right, so if the list is empty, we'll just add our node. Call it link star in equals link. And info equals D. And next equals and previous equals 0. If the list is empty, the head and the tail are in and we're done. Otherwise, we're just going to add to the front. right, so n next equals head. I should put curly brace in here. Our existing head's not a null pointer, so we can go ahead and link that to n and update the head. W linked list. Nothing terribly exciting about that one. Yeah, null pointer, null, null, zero, whatever. Null, PTR, null. I don't care which way you're tracking null. As long as you're internally consistent within your application, it should be happy. All right. So let's see what my autograder thought about my answer. Did I make a bug where there wasn't a bug? The correct answer was zero. I was just trying to lead us astray. All right, no bugs. All goes to zero at some point. All right, so our recursive function. Function, right? -5. Inline. Function 5. All right, so 0, 0. Negative numbers going towards 0. Get 0 out a couple of times. 5 going towards 0. Get 0 a couple of times. So numbers size. First equals numbers 0. Int second equals numbers. Size divided by 2. And last equals numbers. Size minus 1. If first is less than second and first is greater than last, turn first. If second is less than first and second. Second is less than first. Yeah, get my brain here working. Second is greater than first and second less than last. Return second, otherwise turn last would be, assuming my code is looking good first, less than second, greater than last. That seems kind of right. Well, we don't need 8. 3 should be good enough. So that should give me a 2. Numbers 1, 2, 1. Well, they'll all give me a 2 as I use those numbers. Whatever. That's what I did in the chat. Let's leave it as such. 3, 1, and 2. Numbers 1, there's 3 of them, and the line. 1, 2, 3. Right, so in all 3 cases, the median is 2. Right, so we will not take 3, we will not take 3 in these selections, or 1, 1, or 1, right? 3 is never the answer. Assuming my code is working. Yes, can't copy paste without renaming things properly. I do have a bug saying to use 3 there. I got 2 and 3 here, so I got first is 2. That's the one's false. 2. Yeah, whatever my bug is. That's the point. Assuming my code was good here. Probably need a third condition here. So I need first less than second. First less than last. Oh, why does my brain not want to sort? My brain doesn't want to sort right now, apparently. That makes first the smallest. All right, I'll do and last less than second. Let's cheat and just test, see if I get all my 2s that I want. Nah, I just broken things. I'm just breaking things. Probably be easier if I just sorted the array and selected the middle index. But right, it's all based off of the value at that position. And 22 is not 22 is less than second and first, so it's not selected. Position is considered, but not going to be a pivot. All right. Other questions on the test? All right, so that one remains to be graded. I'm still grading. Well, I haven't started grading program 2 yet, so program 2 is up next. And the grading queue first. And then test 2 will be coming along. I've got a minute to spare. Any questions about the test or anything else for tonight? All right, 22 is not the median. The median would be selected. All right, my code's bugging me now here. I need get my brain to work. 1, 2, 3. So first less than second, second. First less than second is false. So that's not my median. If second is less than last, turn second. Otherwise, return last. Otherwise, we have second less than last. All right, so here we're in my else case. So we have second is greater than first. So if second is less than last, return second. Maybe that'll work. That's what we have unit tests for. We're getting there. Need more scenarios. It's terrible. Bugs. Bugs are ruining my day. Yeah, it needs to be the actual median. Right, the practice test, it was the median value. Yeah, for multiple answer questions, a wrong answer will offset a right answer. P is always an int. When a variable is a type, Right, so this is just integer math. An integer divided by an integer, any operator integer is going to be an integer. The only way for this to be stopped being non-integer is if one of the operands is an integer. What's the average on the test? I don't know. It doesn't calculate averages until overnight batch processing is done. You should be able to see that tomorrow if you look at, let's go, go into, where are we? Fall. See what we can see. Test one. I could have swore it showed the average at some point, somewhere. Back to all. Ah, student test result. Does it show you the statistics when you click on this box? Yeah, okay. Just hiding things. Yeah, test two, it'll start showing it tomorrow, and then it'll change as I grade the last question. Yeah, test two is harder than test one because test one is all our linear stuff. Test three is going to be harder than test two because now we're talking about tree stuff, which takes nonlinear to another dimension. And then test four is the hardest test, and then test five, we get a little bit of a reprieve because test five is probably somewhere between test one and two difficulty. Hashing and memory stuff is easier, right? Traversing a tree is a fair bit more involved than traversing an array. So make sure you're practicing your algorithms and you're building your trees for the next test. Should be in 3 weeks. Double check. Yeah, next test in 3 weeks. All right, test every 3 weeks. And before you know it, we'll be done. All right, halfway done through the course. So we're about halfway done through the materials. Yeah, the average test score tends to shrink a little bit. Sometimes test three average will be higher because uh, test one's easy by comparison compared to test two, and people are like, oh no, I need to study more. So sometimes it'll go higher on test three, but typically it'll go lower. What was the average for test one? Probably like 90%. Test two probably be like more like 80%. Yeah. Yeah, I expect the average on this one to be at least 4 points below test one, but it's probably still above 80. We'll see. Time will tell before too long. All right, that's all we have for tonight. I'll post some links. The average have to be like below 68%. If there's a particular question where the statistics for the particular question are abnormal, Then we can do like an extra credit quiz on that topic area. Try to offset. Sometimes the wording on questions is not quite ideal. It's a problem when you use English in composition with computers, which are far less ambiguous, whereas the English language has plenty of ambiguity. All right, I'll post the links. Make sure you check that out. Get some reading. Make sure you start to get a handle of the terms for graphs. And we'll be talking about that for a couple weeks.